7-7, and we're talking about kinematics. Almost not right. I will learn how, you guys will learn how math connections, how math connects to the motion of an object. Listen, y'all, listen, it's been one of them days. How math connects to the motion of an object, okay? So we're talking about how a particle can move, okay? How a particle can move. First of all, let's talk about what it is, okay? It is the study of motion. It is the study of motion, okay? So we're gonna take into account not only distance that this object is gonna travel, but also the speed as well as its direction, okay? So we're gonna take into account both of those things when we're talking about kinematics. This will lead us to functions for displacement, velocity, and acceleration, and their connection to calculus, not just integration, but also derivatives as well. This is where, like, we've gone through like pretty much like the basics of integration, where it's like solely integration. Now it's going to be the combination of the two from here until we get done with calculus, okay? So a few things we need to define. So when we have an object that's in motion, the distance that it travels accumulates over time, okay? So that's whether the object is moving to the right or to the left, the total distance is going to go is accumulated over time. So whether it's moving to the right or to the left. The speed that the object is going is how fast it is traveling, okay? I think everybody knows that that's what speed means. So when we talk about speed, how fast the object is going. The displacement of an object, the displacement is its position relative to a fixed origin O. So it has its initial starting point, okay? And the displacement is where it is at different points in time along its path, okay? The velocity is its rate of change of displacement. Now you've heard this word before, or this combination of words. What does rate of change mean? So yes, velocity is the derivative of displacement. And acceleration is the rate of change of velocity, or in other words, it is the second derivative of displacement, but it is the first derivative of velocity. Just a few terms there to define, okay? So let's start at the beginning. Start with displacement. The displacement function is indicated with S of t, okay? So anytime you see S of t, we're talking about displacement. If S of t is greater than 0, so it's some particular value of t, if S of t is greater than 0, then the object is to the right of the origin. But if S of t is less than 0, it is to the left of the origin. A motion diagram is a visual that plots the position of the object on a single number line. And what you see down here is an example. On this horizontal axis, we actually have its position, okay? And then the above arrow represents essentially the direction it's heading in different time intervals and where the location is of the object after certain time intervals. So as we can see, at 25, this could be meters. So it started to 25 meters from the origin, from some fixed point when it initially started, okay? It traveled to the right for 2 seconds and ended at 45 meters from the origin after 2 seconds. Then it changed direction and went back to the left, and at 5 seconds, it was back to the origin. And then at 6 seconds, it was 35 meters to the left of the origin. Not negative 35 meters as like you know, distance is positive, it is 35 meters to the left of the origin. Okay? So far, so good? Yeah. So far, so good?
Yes.
Yes. Thank you. All right, here's an example. As you guys know by now, get down what's important. If you want to go back and get the details of each part of each question, you can do that by going back and rewatching the video. I haven't recorded for the last, 2 months, so the videos are getting posted. An object travels with a displacement function S of t is equal to 5 minus t centimeters for t is greater than or equal to 0, but less than or equal to 10 seconds. So we have this nice function right here. Find the initial displacement of the object. Initial displacement means what? S of 0. our starting point, when time is equal to 0. So anytime you see initial, that is when t is equal to 0. If it doesn't tell you anything about finding the initial displacement, or it doesn't say anything about its initial displacement, you can assume that its initial displacement is 0.
Always.
Okay, always. If it doesn't say anything, it doesn't provide you any information, or doesn't ask you to find it, you can make the assumption that the initial displacement is at 0. But here we are finding when t is equal to 0, so that's just going to be 5 centimeters. And more specifically, it's going to be 5 centimeters to the right of the origin. Very good. Then part B, we have to find the displacement of the object at the time t equals 3 seconds and t equals 10 seconds. So, I mean, this is a very simple function, y'all. All right. What kind of a function is it? Keep that in mind. Keep that in mind, it's a linear function. So, at 3 seconds, displacement is 2 to the what? To the right of the origin. And at 10 seconds, it's gonna be 5 to the left, because when you plug in 10, it's -5, right? So then it's gonna be 5 centimeters to the left. We don't put -5 centimeters to the left. The negative indicates that that's where we are, position-wise. Now part C asks us, at what time does the object reach the origin? How do I find that?
Set the function equal to 0.
Exactly, because we're trying to figure out when position is at 0. So we set the function equal to 0, and we find out that after how many seconds?
5.
The function is at the origin. Does the object ever change direction? Explain your answer. Why?
2 to the right. 5 to the left.
So you're saying yes, it changes direction?
No.
Because it starts from 5, it just goes to the left. Because you're going left because it's negative centimeters in direction.
But also, what kind of a function is this?
It's a linear, so it's not gonna curve.
It's a linear function, so it never curves, so it ain't gonna change direction. It's not gonna have any of those turning points. Yes. But true, also what you said about the fact that it's starting at 5 centimeters to the right of the origin, is continuing to head in one direction.
What kind of function was that example question? Like,
Oh, so I'll go back to that and talk about that one. So it doesn't turn, no turning points. Lastly, E, our motion diagram. To show this information that we found, we know that we're going to have a horizontal line that represents our position. We need some key points on here. We know, first of all, we always need some origin, okay? And we need, what other numbers to represent our position? We need a 5. We need a -5. And we need a 2. I think that's it. Yeah. So where did we start? What was our initial displacement? At 5 centimeters. And then at 3 seconds, we were 2 centimeters to the right. So we were going this way. So at t equals 3 seconds, this was t equals 0. So at t equals 3 seconds, we were 2 centimeters to the right. And at 10 seconds, we were
origin? No, wait.
5 to the left.
5 to the left.
What is it?
But it's still a line.
The thing is, it doesn't change direction. It's still heading in the, it's still heading technically to the left over time. Because it starts here, heads to the left after 3 seconds, 10 seconds, is still heading towards the left. Make sure that you do include arrows to indicate its direction in which it's heading. Now for the last example, because there was a turn, that let us know that whatever the function was that represented that motion diagram, drew a blank, sorry. It did have a turning point because it originally started going to the right and then it changed directions and went back to the left. So as you can see here, we started 25 meters to the right of the origin. We started heading right, and then at 2 seconds, that's when it changed direction and started heading back this way.
So is that, wouldn't the first part of that be a, like what kind of function would that be?
That would be like a quadratic.
Quadratic?
Mhm.
Okay.
Because at one point we were increasing and then we went to decreasing. So we went one direction and then we changed and went the other direction. Any questions on displacement?
Oh.
Velocity, we know, is the rate of change of displacement, AKA the derivative. You do have average velocity and you also have instantaneous velocity. Average velocity is essentially old school slope where you're finding the slope between 2 points on average from one time to another time. That's what S of T sub 2 minus S of T sub 1, the position at one time minus the position at another time, divided by its actual times, the change in time. And here's a diagram to represent that. So AKA old school slope. Instantaneous velocity is how fast it's going at a particular second, not over time, but at a particular second. Instantaneous velocity, again, this is known as your velocity function. When you are taking the derivative of displacement, you are finding the velocity function, you are finding the derivative of displacement. It is the gradient of the tangent line on your function at any given time. It is measured in meters per second. So whatever values that you get when you are finding the velocity at a particular time, it is in meters per second. A few things that you do need to make a note of is that if velocity is greater than 0, the object is moving to the right. If velocity is less than 0, the object is moving to the left. And of course, if the velocity is equal to 0, it is neither moving any direction, it is at rest. It is at rest. Okay? A change in sign of velocity indicates that the object has changed direction, similar to displacement. Well, no, actually, no, not similar to displacement. My mistake. So let's look at this example. It's a tad bit small. Let me make it a little bit bigger. I didn't realize how small it was once I did it this size. Okay. Interval. So that error. Okay. That's better. Okay. A particle moves in a straight line with displacement from O, some origin. Given by the equation, S of T is equal to 3T minus T squared meters at time T seconds. T is greater than or equal to 0. I did not put that in there, but it is. We want to find the average velocity for the time interval from T equals 2 and T equals 5 seconds. And then we also want to find instantaneous velocity at T is equal to 2.
Wait, what were the values again?
T is greater than or equal to 0. Oh, we're going from 2 to 5 for average velocity. So make sure you're aware of that. Average velocity, instantaneous. Average is old school slope. Instantaneous is the it's the derivative. The average velocity. So I need S sub 5 minus S sub 2 all over 5 minus 2. What did you get? Negative 4.
Meters per second.
Meters per second. Yes, that's your average velocity. Okay, what about your instantaneous velocity?
-1.
-1. Very good, because remember, you need to take the derivative of displacement. What was your derivative?
Negative 4. Wait, hold on. Sorry, negative 2t plus 3.
So then you would evaluate your velocity at that particular time, and that's how you get -1. Now, what does that represent? It represents 1 meter per second, but it's to the left of some fixed point. Okay. Very good. Now, what you do, of course, as you can already sense, when you differentiate displacement, you get velocity. When you integrate velocity, you get displacement. The change in your displacement is either the time or your position at one time minus the position at another time, or the integral of velocity from T1 to T2. That's your change in displacement. Okay, so again, that's your change in displacement, the integral from one time to the second time of velocity is how you figured that out. You can also figure out in the T sub 2 minus T sub 1. There's also this concept of the total distance that an object has traveled over time, okay? Is your change in displacement, your total distance that is traveled. We change direction on an interval, the velocity will change its sign, and in a sense affect, the distance that we travel as well. To find your total distance traveled, we need to add the components of all the areas above and below your time axis, if it's graphically, okay? The same way that we would find the area underneath a curve, we were just doing standard integration, okay? So distance traveled is the area above and below your t-axis, because we don't have x, we have time and velocity, okay? And another way it can be found as well as doing the integral from time 1 to time 2, the absolute value of velocity, okay? That is how we find distance traveled. So we're going to take a look at this example. The velocity time graph for a train journey is illustrated below. The total distance traveled by the train is what we have to find. Of course, there's no function that represents the train's path over time, but you use the concept of distance traveled and the fact that you need to find essentially the area underneath or above the curve. Luckily for us, all the area is above the curve, so that means they're all going to be, all the areas are going to be positive. And you just probably want to create some geometric shapes the same way that we did when we were doing integration, okay? How should I split this up?
Triangle.
Huh? A triangle?
Yeah, we made a triangle.
And a
Right
rectangle.
there, a right triangle.
Rectangle?
Trapezoid? No.
I mean, there would be a,
Th-
yeah, if you
that-
connect right there, you can make a triangle, and then that would be a quadrilateral of some sort.
I just make a triangle square and then.
Yeah.
Triangle and trapezoid.
Or a triangle, and, I mean, two triangles in a square, like Jonathan was saying. So like 0.430.
No,
I'd
you
make,
don't
okay,
do that.
I'd make 3 triangles and then 2 rectangles.
Yeah.
Yeah.
Yeah,
3 triangles and 2 rectangles?
Yeah.
Literally.
So like from point 1, that would be a triangle front, and then point 3 would be a rectangle. And then at 30, like that, that'd be a 4, and then that.
Yeah, that was so much simpler.
That's what
Yeah.
Lily was talking.
Sorry, I was just.
Every time you go into the third person, it's so
Exactly.
disconcerting.
I don't
So
even
you
recognize
forever.
it.
All right, either way you do it, whether you did 3 triangles and 2 quadrilaterals, or if you did some trapezoids, some triangles, whatever, you'll still end up with the same area, okay? You just need to know the formulas for these different areas. What's the area of a triangle? My base right here is 0.1, my height is 50. All right, then I got this quadrilateral here. That's nothing but base times height. So that's going to be 0. For my base, and my height is, okay. Now I got this little triangle right up here. So that's 1/2.
20 times 20.
My height times 0.1. I got another quadrilateral. That's 0.2 times 30. And then I have a triangle, which is 1/2. 0.1. My height is 30. Okay. This could very well be done without a calculator because 0.1 just means you move the the decimal place of the bigger number over. So this ends up being half of 5. So that's 5 and 5 halves. Then I need, what's 50 times 0.2? What's 1/5 of 50? 10. And then what's half of 20? Bring over the decimal place. 1. Then 0.2 times 30 is going to be 6. Or what's 1/5 of 30? And then over here, if I move the decimal place over, that gives me 3. And then half of 3. What's 5 halves plus 3 halves? Or, so then my total distance traveled is 21 kilometers because, yep, it's in terms of kilometers. That's using, finding distance traveled without the equation. Now let's look at an example 1 with an equation. Shoot. A particle P moves in a straight line with velocity function given to us, in meters per second, of course. It asks us to find the times when P reverses direction. When it reverses direction, you essentially are looking at velocity at different times, correct? In order to determine where velocity is going to change direction, we probably need to figure out where velocity does what?
Equals 0.
Where it equals 0, where it's at rest. Because we can figure out where it's at rest, we could probably see if in between those respective intervals it is going to be changing direction. Okay? Because remember, if velocity is greater than 0, it means it moves to the right. If velocity is less than 0, it means it moves to the left. So if I can figure out velocity equals 0, then I'll be able to determine in between those breaks if it's changed direction or not. So that means we need velocity to equal 0. Solve this out for me and give me my times when velocity, the object's at rest.
Negative, well, yeah, no, it's 2 and 1 because t minus 2, t minus 1.
Yep, t minus 2, t minus 1, so that's t equals 1, t equals 2. Okay, and just to double check this, this is still where t is greater than or equal to 0. I did not include this in any of the questions, so I didn't want to pull in the symbol. If I start at 0, I got 1 and I got 2. If I were to plug in 1/2, is that positive or negative?
Positive.
If I were to plug in 3/2,
Well, if it changes direction, or does it hold?
Yeah, you said 3 times. Yeah, it's still positive.
Positive. Yeah.
Oh, no.
Okay. So
That's
now
still
we're-
positive.
it's negative. 17 minus 18?
Oh, never mind.
So it's negative, yeah. So it changes direction, it reverses directions at 1 and at 2. So yes, those are the 2 times when it reverses direction at t equals 1 second and t equals 2 seconds. Just because you factor or just because you find the values of t doesn't necessarily mean that it's changing directions. You want to double check it. Kind of the same way when we were doing derivatives and we set this first derivative equal to 0 and we did the number line to see if it's a max or a min. Just because it's where the function equals 0 doesn't mean that it necessarily makes a hill or a valley, okay? Hence it says find the distance P travels in the first 4 seconds of motion. How do I find the distance traveled? Integrate. Did y'all write it down on the last slide, 2 slides ago?
Integrate the velocity function between the bounds.
Integrate my velocity function between my bounds. Okay.
Is it the displacement function you have to integrate?
No, it's the velocity function that you would integrate. But the thing is that you have to take into account the distance of each time interval. So from start to 1, from 1 to 2, and then from 2 to 4. Because you have these different times where it's changing direction, so you have to figure out the distance it traveled. So if you were talking about doing the integration of your velocity function, you have to take into account that you start at 0 seconds and then you change direction at 1 second. Then you have to take into account that you're going from 1 second to 2 seconds, another direction. And then take into account that you're going from 2 seconds to 4 seconds of another direction.
Where's the fourth one?
First 4 seconds.
Or
Or,
or you can do the S of T2 minus S of T4.
that's what this is.
Oh, dang.
Hold on.
You wrote it down. It's the absolute value of velocity. So I can find the total distance traveled doing the absolute value of my velocity function for the entire interval from 0 to 4. Because even though I know I'm heading to the left from 1 to 2, it takes into, by taking the absolute value of that, it's turning it positive and then continuing to add it to whatever the distances covered when we went to the right, and then from 0 to 1, and then to the right from 2 to 4. Okay, so we cannot do this by hand. Distance traveled in a calculator question is going to be done that way. If it was on a non-calculator paper, we would have to do it the top way. Okay, and this is a easily anti-differentiated function that we plug in each of these values for. Okay, but going to use our calculator here. Bless you. All right, so we're going to do the integral. How do I access the integral? Math 9. I have my bounds from 0 to 4. Remember, by doing the absolute value of velocity is taken into consideration from start to my first 4 seconds. Anybody remember where absolute value is located? Math.
And upper one, and right there.
Yep, under number, math number. So then I type in my velocity function, x squared. Of course, y'all know we can't use t, but we know that x is representative of t. Don't forget our dx. And then we graph. Oh, not graph, I mean enter. So that's our total distance traveled. 5 2/3, 5 point, if I wrote 3 significant figures, 5 point what? 6'7" or 17/3 meters. Yeah.
So 17/3 would be a better number.
Mm-hmm. That way we won't have to worry about any 3 significant figure on it or anything like that. Now it asks us for our change in displacement over the first 4 seconds. Change in displacement is what formula?
It's the same thing, just not absolute value.
Or the S of the T2 minus the S of T4, right?
Yep.
Yeah.
So first 4 seconds, T2 would be 4, T1 would be 0. So then I just need my displacement function. Plug in 4, plug in 0, and get that. Essentially, I'm going to have to do the integration of this function, okay? So running out of space, it's okay. This is my function, t squared minus 3t plus 2. What's the antiderivative of t squared? Antiderivative of negative 3t.
-3 of 2x
And what's the antiderivative of 2?
plus 2x.
T.
Sorry.
We're going to integrate that from 0 to 4, okay? So when I plug in 4, that is 64 over 3 minus 48 over 2 plus 8 minus 0 because when I plug my lower bound, I get 0. Find that value so I can get my change in displacement over the first 4 seconds. It is 16/3 meters. Because this is talking about displacement, are we to the left or to the right? We are to the right of the origin. Okay, because we're talking about its displacement. Where is it located? Where is its position in relationship to the origin? All right, acceleration, the last little bit. That is the change of velocity. It is the antiderivative. No, it's not. It is the derivative of displacement. Second derivative of displacement, first derivative of velocity. Of course, you can have average acceleration. The similar is old school slope, except using velocity. And of course, the acceleration function is the first derivative of velocity, second derivative of displacement. And as we know, differentiate. If I go to the right, displacement, velocity is the derivative of displacement, acceleration is the derivative of velocity, and of course I can go backwards.
What's beyond acceleration?
Something that doesn't deal with motion.
Super acceleration?
That is beyond me. Beyond this course. Okay.
Hard to use google.com.
I'm about to say that would be a Google question. All right, we ready?
Mm-hmm.
I think the one that I want to do is
Frantically goes back.
is this one. This one is a calculator problem. It says the train is initially at rest at the station. It begins to accelerate according to the function a of t. Find the velocity function of the train and sketch its graph. Well, we know that velocity is nothing but what of acceleration? It's the antiderivative. Okay? And the thing is, we don't have any bounds here. That's fine. Okay, we're looking for the general function anyway. We're not finding for the specific value. Okay? So what is going to be the antiderivative of 1/2 e raised to the negative t over 100?
Your a term is 1 over 100.
Yep, your a term will be 1 over negative 1 over 100.
Yeah.
So that'd be negative 100.
So negative 50.
So negative 50 e to and then plus c. Now I do need to find my value of c, which is going to be what? Or how do I find it? What do you know about this train?
It starts at rest.
It starts at rest. Rest is when velocity is equal to 0. Okay? So
Starts out at 0.
and it starts out at 0. So c is equal to 50. Exactly. So my velocity function is negative 50 e to negative t over 100 plus 50. Of course, we will need to plug that into our calculator to get a sketch of that. When I plug this in, I'm definitely going to have to adjust my window. Because x represents t for time, what should my x min be? 0, because I'm talking about time. I can't have negative time here, so it got to be 0. Give me a good x max.
65.
65? Cool. What about my y min? Well, y represents my velocity. Okay. You wanna play around with it a little bit?
Sure.
Okay. So I definitely should change it, probably my min to 0.
Mm-hmm.
Okay.
Well, this goes down. Wow.
My y man should be, oh, not my y max. My y man should be 0. Maybe 50. It looks like it's kind of shooting off in the direction.
Maybe it plateaus.
Maybe it plateaus. Let's open up my x max a little bit bigger. Let's make it 100. Looks like it's just steady increasing. Looks like it's just steady increasing.
There it is.
Here we go. So, starting at 0, and it's increasing. It is a sketch where my y-axis should be labeled what, and my x-axis should be labeled what? And t. Very good. Now, how long will it take for the train to reach a speed of 40 meters per second? What does that mean? My v of t equals 40. So that means I need to set the function equal to 40 and I need to solve it. How would I do that? Huh?
You could.
I could try 50 over, but then I'm gonna have to do what?
I'd try 15 and divide by and do 4 fifths.
Divide by negative 50. Then I'll have to do what? To get rid of the e. ln, and then I'm going to multiply by negative 100 to find my time. I'm going to use my resources. I'm going to plug in 40, and I'm going to find an intersection point right there. It's the same thing, same thing. But by me setting up this equation right here to say that it equals 40, and using the calculator to get my answer, I will still get the same marks as those who do it by hand. So around the 3 significant figures is going to be 161 seconds. Oh, it is kind of small for y'all, isn't it? Good stuff. I could even add into my graph that this is 40, and I'm looking for that intersection, and boom, I get even more method points.
Really?
Yeah.
That's even more method. Look at that.
Okay. How far would the train travel in this time? How far? How do I figure that out?
You find displacement, right?
I would find displacement of what?
Of when the velocity goes.
Oh,
So you have to plug in 161 seconds.
I have to plug in 161 seconds.
And then
You have to put it
you gotta integrate that one.
Now I gotta integrate from 0, where it starts, to that time for my velocity function. Okay? Now the one downside about using my calculator, I got a rounded bound.
What does that mean? Oh.
A rounded bound means I'm gonna have a rounded distance of further and further away from the more accurate number. Unless I go back to my calculator and I use all these decimals, then that way I'm not as far off from it.
I would do it.
You know? Okay? So I'm looking for the antiderivative from 0 to 160.94379 ... of my velocity function. And you can do that. You can do v of t because you've labeled your v of t. You don't have to rewrite the function. You can do that.
Oh my goodness.
And then I'm gonna use my calculator to do this somewhere. All right. It's not being lazy, it's being smart, okay? All right. Y'all know I hate using my calculator, but right now my back is screaming. I'm ready to sit down. The more numbers you have, at least the closer you are to being more exact. But of course, if you do it by hand, you will have the most exact possible function or value of t. So you can use that. And did I type it in correctly? I think 50e to the Yep. How far did the train travel?
Always 400.
course. 4,050
4,000.
meters. Speed measures how fast something is traveling regardless of the direction. Okay, the speed limit, how fast you should be going when you're driving. It is a scalar quantity that has no size, but it has a size but no sign. Okay, so that it cannot be negative. It cannot be negative. Speed is the absolute value of velocity. Okay, so when you're taking the absolute value of the velocity function when you're finding the distance traveled, okay, you're taking finding the integral of speed. Something that you need to be aware of, though, when you are talking about speed or when you're looking at speed is that there's a comparison between velocity and acceleration that lets you know whether or not you're speeding up or slowing down. Okay, so you gotta look at velocity and acceleration to determine the speed of a particular object. So to determine when the speed of object is either increasing or decreasing, you look at the sign of velocity and the sign of acceleration at that particular time. And by sign, I mean whether it's a negative number or a positive number. Because if the signs of velocity and acceleration are the same, then that means the object is speeding up. But when they're different at that particular time, then it's decreasing and slowing down. So you're gonna probably be asking some shape, way, or form to find the velocity at a particular time and to find the acceleration at a particular time. You'll know if the object is speeding up or slowing down by comparing the signs of those two at that particular time. So if they're both positive or if they're both negative, the function is speeding up. But if one's positive and one's negative, then it's actually slowing down. A particle moves in a straight line with position relative to O given by the displacement function, t to the third minus 3t plus 1 centimeters, where t is the time in seconds. This is a non-calculated problem, so I'm going to go ahead and close this off. We are going to find the expression in the sign diagrams for velocity and acceleration. The sign diagrams are going to let us know if we're changing directions. It's also going to help us determine the speed of whether the speed is increasing and things like that later on by looking at the changing of the signs. So I need to find velocity. What's the velocity function?
3t squared.
And what's the acceleration function?
6t.
There we go. We need to find our sign diagrams, which means I need to set both of these equal to 0. So when the velocity is equal to 0, t is going to equal what? Huh? Plus or minus 1? Very good. And when acceleration is equal to 0, t is equal to what? Is equal to 0. Okay, so then for our sign diagrams for velocity, yep, 0 and 1, and then acceleration, we'll just have 0. So for velocity, less than -1.
Oh.
Okay, is it positive or negative?
Nice.
-3/2. It would be positive.
It'll be positive. Okay. If I plug in -1/2, negative. Positive 1/2 is still going to be negative, and 2 is going to be positive. When I plug in acceleration, when I plug in a negative number, it's going to be a negative. And now I'm plugging a positive number, it's going to be positive. So there are my sign diagrams as well. Now it says find the initial conditions and hence describe the motion of the particle at this instant. The initial conditions means you are finding S of t. You're finding S of 0, V of 0, and A of 0. So in that way you know where it's located at 0 seconds. So where's it located at 0 seconds? That's a 1. That's a 1. So it's 1 centimeter. Velocity initial velocity is what? -3 centimeters per second. And then acceleration is 0. Okay, so acceleration is 0. So what does this tell us? That means at 0 seconds, we are located.
Can we say that we're slowing down?
It's not
I
slowing
mean,
down. It's just
technically-
going left.
Technically.
It's going left for sure because velocity is negative. So it's going to be one centimeter to the
Right.
of the origin, and then heading left at a speed of
3 meters per second.
3 meters per second.
It wouldn't be constant.
It is because your acceleration is 0. Acceleration is like if you're getting faster or slower. So if it's positive, you're getting faster. If it's negative, you're getting slower. Velocity is just which direction.
But
how
in
fast
real
you
life,
move, right?
you can't keep, it wouldn't stay in motion.
It's at that singular incident can. It's just it's literally
But
for
it's
like
like
0
zero.
time.
I guess in the, okay, I guess in this specific moment.
Mhm.
Sure.
Yeah, this is at the specific moment. It's 1 centimeter to the right of the origin, heading 3 centimeters to the left, 3 centimeters per second to the left. Describe the motion of the particle at t equals 2 seconds. So what's happening describe the motion of the particle at 2 seconds. What's that mean? We have to plug in 2 as well. So when I plug in 2, running out of space. No. Okay. So for part C, what's S of 2? 3. What's V of 2?
Oh, wait, no, not 9. I had some.
It's 9.
Oh.
And then what's A of 2? 12. So we found all those. Let's describe the motion. Okay, describe the motion. So at t equals 2, we are 3 centimeters to the right, heading which way?
Oh, well, yeah.
Heading to the right at how at 9 centimeters per second. So that and we are accelerating, or we start speeding up. Or increasing speed, speeding up, increasing speed.
But I can still be accelerating.
Because the signs are both positive. Remember, when the signs are positive, that means the sign of velocity and acceleration, that means we're increasing in our speed. Now, D says find the position of the particle when it changes direction. Okay, so it changes direction in 2 different places, does it not? At what times does the particle change direction? No, when it equals 1. Okay,
Oh, right.
so then that means I have to do what? To find the position of the particle when it changes direction. I gotta plug that value into what?
Yes.
S of t. So to find the position of the particle and it changes directions in -1 and +1. So S of 1 will give me 1 minus 3 plus 1, so that's -1. And what's S of -1? 3. Now you gotta draw the motion diagram to represent this. Okay. What's happening at 0?
The velocity is going to the left.
Okay.
but
It's not accelerating.
It's not accelerating, it's not decreasing, it's not doing any of that. So, which values do I need on my S of T? So -1. You said in 3. You said 1. No, we don't have a value for 1. I mean, we probably could include it, maybe. I mean, we could actually include everything in between since it's a small area. Where do we start?
So we start at 1.
We start at 1 centimeter, because that was when T was equal to 0. And then we started heading in what direction from there? We started heading to the left. Until when? Until 1, -1 when we changed directions, didn't we? What time were we at -1? 1. So I was heading to the left. Then I changed directions to head to the right. Do I have any other stopping points, changing points, anything like that? Said 2. No, 2, I was, well, after 2 seconds, I was 3 centimeters. So that's 1, 2, 3. So I'm here at 2 seconds, but I'm still headed to the right, am I not? So I don't think I changed any other time after that, right? I got 0, 2. And to the right. If the particle is speeding up, I want to say article, if the particle is speeding up, that means that velocity and acceleration are the same sign. So where are they speeding up? Or where are they increasing? Look at those sign diagrams right here. -1? Only after, is it after -1?
Can you do like T is greater than
T is greater than -1. But less than what? Look at those sign diagrams, you guys. I should have lined up my zeros, okay? When acceleration is negative, that's everything less than 0. If I look less than 0 on velocity, are the signs ever the same?
So T is greater than -1. T is greater than. Because that would be after 1 is positive on both.
-1 to 0. And then what about 1?
T greater than 1.
It'll be equal there because they both have the same value. Let's see, -1 would be there. Because the signs are the same in those respective intervals. Signs the same for those respective intervals.
Would that be T is greater than equal to
No, because the signs are different there.
Okay.
That's where like it changes.
Oh,
That's where it's
okay.
at rest there. And then here, the reason why it'll be equal to 1 is because essentially, well, actually no, yeah, it'll be equal there because they're both on the positive aspect. And that is motion, particle moving.